Welcome to The Explainer. I am absolutely thrilled you're joining me today because, well, we're going to unpack something that is literally sitting in your bathroom right now. Something you probably take completely for granted. You know the drill. We've all got that bottle of ibuprofen, aspirin, or naproxen sitting in the medicine cabinet. We pop a pill when our head pounds or our joints ache, and miraculously, the pain just fades away. But have you ever stopped to wonder how these common painkillers actually work on a molecular level? Today, we're going to completely demystify the incredible medicinal chemistry behind nonsteroidal anti-inflammatory drugs. You probably just know them as NSAIDs. To really guide our exploration today, I want to throw a slightly provocative question your way. Why does the exact same pill that cures your headache sometimes completely ruin your stomach? That right there is the fundamental conflict of medicinal chemistry we're digging into. It's an amazing story about molecular locks and keys, totally unintended consequences, and this relentless quest for the perfect drug. So here is our roadmap for today. First, we'll look at the chemistry of pain. Second, how traditional NSAIDs work. Third, the COX-1 versus COX-2 dilemma. Fourth, designing a better key. And finally, number 5, the side effect trade-off. Okay, let's dive right into part 1, the chemistry of pain. To actually figure out how to stop pain, we first have to understand how our bodies create it in the first place, right? Whether you stub your toe or catch a nasty bug, inflammation doesn't just happen out of nowhere. It is a highly coordinated chemical cascade. The whole process actually kicks off right at the cellular membrane. When there's some kind of inflammatory stimuli, like a physical injury, an enzyme called phospholipase A2 releases this molecule called arachidonic acid from our cellular membranes. Now, that arachidonic acid, that's the raw material. It's the fundamental building block for your entire pain response. From there, it gets grabbed by a super crucial family of enzymes called cyclooxygenases, or as we'll call them, COX enzymes. Let's break down exactly what that COX enzyme is doing, because it basically operates like a dual action factory. First, the arachidonic acid is released. Then, the COX enzyme takes it and converts it into a highly unstable molecule called PGG2. Almost immediately, it acts as a peroxidase to convert that into PGH2. And finally, this PGH2 becomes active prostaglandins, like PGE2. And those prostaglandins, those are the actual culprits causing the fever, the swelling, and that awful throbbing pain you feel. Now here's a really fascinating detail. These prostaglandins act as local alarms in your body, but they have a remarkably short half-life. We're talking just 1 to 5 minutes. Why so short? Well, because the body essentially built a self-destruct timer into these signals to prevent runaway systemic inflammation. They're only meant to act briefly and locally. And this is exactly why blocking their production right at the source, at the COX enzyme, is such a highly effective way to stop pain. Think about it. If you shut down the factory, those existing alarms are going to fade out in just minutes. Which brings us to part 2, how traditional NSAIDs work. So how did we actually first learn to shut down this chemical factory? Well, think of the COX enzyme like a lock, and the arachidonic acid as the key that turns on the pain. Traditional NSAIDs physically block the lock's keyhole. We call this the hydrophobic channel of the COX enzyme. If you look at how aspirin works, it literally sneaks into the channel and transfers its acetyl group to a specific serine residue, serine 529 if we're being exact. It acts exactly like a broken key jammed in a lock. It just completely obstructs the arachidonic acid from ever entering. But, here is where we hit a classic double-edged sword in pharmacology. Most of these traditional NSAIDs, your ibuprofens or diclofenacs, they're acidic. They form a really strong ionic bond with an amino acid called arginine 120, right at the entrance of that COX channel. Now, this strong bond is exactly what makes them so incredibly potent. But because they're weak acids, when you swallow them, they diffuse into the lining of your stomach. They become ionized and they get chemically trapped there. We call this ion trapping. And it causes direct damage to your gastric mucosa, your stomach lining. So the very thing that makes the drug so powerful is exactly what's ruining your stomach. To understand how drug designers fought back against this stomach issue, we need to quickly chat about a concept called steric hindrance. In chemistry, this basically means using big, bulky molecular groups to purposefully force a molecule to twist into a highly specific 3D shape. Think of it like a guy with really broad shoulders trying to shove his way through a narrow, crowded doorway. He has to twist to fit. Check this out to see what I mean. If you look at this simple, linear structure of aspirin compared to a much more complex NSAID like indomethacin, the difference is wild. See that bulky piece hanging off indomethacin with a chlorine atom? That's a p-chlorobenzyl group. Drug designers intentionally attached that massive group right there to create steric hindrance. It physically bumps into the rest of the molecule, forcing indomethacin to twist itself out of a flat shape into the absolute perfect exact 3D shape needed to jam itself deep into that COX enzyme. It is literally molecular origami. Let's move on to part 3, the COX-1 versus COX-2 dilemma. Okay, so as our molecular origami got better and better, scientists stumbled onto a massive complication. It turns out there isn't just one COX lock. There are two. Enter the concept of isoenzymes. These are basically enzymes that might look just a little bit different in their genetic sequence, but they catalyze the exact same chemical reaction inside your body. So as it turns out, we have two versions of the COX enzyme that do the exact same job, but for entirely different reasons. COX-1 is basically the housekeeping enzyme. It's present constantly, and its main job is to produce prostaglandins that actually protect your stomach lining and regulate blood flow to your kidneys. Pretty important, right? COX-2, on the other hand, is an inducible enzyme. It only really surges during inflammation to cause pain and fever. And boom, this reveals our core dilemma. Traditional NSAIDs are incredibly blunt instruments. They block both. Sure, they cure the pain by blocking COX-2, but they strip away your stomach's natural defense by simultaneously shutting down COX-1. This brings us nicely to part 4, designing a better key. So how did medicinal chemists engineer a drug that only blocks the bad guy, COX-2? Well, take a look at the structures of ibuprofen and naproxen. They're relatively linear, straightforward little molecules. Now compare that to Celebrex, also known as celecoxib. It looks like a completely different beast, doesn't it? It's highly branched, it's bulky, and it has that very distinct sulfonamide group, that piece with the sulfur and oxygen atoms just hanging right off it. And that bulky design? Absolutely no accident. When scientists mapped out the two different enzymes, they found that COX-2 has a slightly smaller amino acid at position 523, a valine, which essentially creates a tiny extra side pocket inside the lock. COX-1, however, has a bulkier amino acid sitting there, which completely blocks that pocket. So Celebrex was explicitly designed with that bulky sulfonamide group, so it acts like a key with an extra ridge. It perfectly slides right into the COX-2 side pocket, successfully blocking the pain factory, but it physically cannot fit into the COX-1 lock. The result? You get pain relief without shutting down the stomach's protective systems. It's brilliant. Finally, let's look at part 5, the side effect trade-off. Now, this selective COX-2 design sounds like the ultimate victory, right? Unfortunately, as we know, biology rarely offers us a free lunch. When we block COX-2 selectively, we end up disrupting a really delicate balance in the cardiovascular system. Here's what happens. COX-1 in your blood platelets produces something called TXA2, which promotes blood clotting. It's prothrombotic. Meanwhile, COX-2 in your blood vessel walls produces PGI2, which prevents clotting. It's antithrombotic. So if you take a highly selective COX-2 inhibitor, you stop the antithrombotic PGI2, but you leave the prothrombotic COX-1 side running completely untouched. You accidentally tip the scales toward blood clots. And this means we are left with a spectrum of some pretty severe trade-offs. Traditional non-selective NSAIDs run the risk of gastrointestinal bleeding and ulcers. The brilliant COX-2 selective drugs? Well, they protect the stomach, sure, but they carry an increased cardiovascular risk for heart attacks and strokes. And honestly, both classes can cause renal issues, like fluid retention, because both enzymes play a role in kidney function. This is exactly why it is so absolutely critical to always consult your healthcare team. The right choice depends entirely on your specific personal medical history. But chemists aren't giving up. They are constantly finding clever workarounds to these side effects. For instance, look at diclofenac. Those two chlorine atoms make it highly potent, but they also draw electrons in a way that makes the molecule susceptible to forming toxic metabolites in the liver. Not great. But then, look at Nabumetone. Notice it doesn't even have an acidic carboxylic acid group on it. It's actually a non-acidic prodrug. When you swallow it, it passes right through the stomach without causing any of that primary ion-trapping irritation. It only turns into an active acidic NSAID once it hits the liver. Talk about a brilliant chemical disguise. Which brings us to the ultimate question for today. Is a truly perfect painkiller chemically possible? Or is relief always going to be a delicate trade-off within the intricate balance of molecular chemistry? It seems like every time we tweak a molecule to avoid one pathway, biology is right there to remind us how deeply interconnected our systems truly are. Thank you so much for diving into this incredibly fascinating chemistry with me. Keep asking questions, and I'll catch you on the next explainer.